Hello everyone. In this lecture we will be finding closed form solutions to the celebrated Cauchy equation. Here's a view of this problem. We would like to find all functions f defined from rational numbers to rational numbers satisfying the following additive equation for x and y rational numbers. In the first step, notice that by plugging in x equals y equals 0 into the equation, we realize we get f of 0 plus 0, which is equal to f of 0, equal to, from the right hand side, f of 0 plus f of 0, which is 2f of 0. From here, f of 0 being equal to 2f of 0, there's only one explanation, and it is that f of 0 is simply equal to 0. So that's the first result that I would like to highlight. The second step, I will prove by induction the following statement, that in fact f of kx is equal to k times f of x for k in natural numbers and x in rational numbers. The result is true for k is equal to 1, so it's easy to check that, obviously. And in the second step, let's assume it is true for k, and we would like to show for k plus 1. In this case, take y equals kx and plug it into our equation, so we get that f of k plus 1 x is simply equal to f of x plus kx, and that's equal to, so we can use the definition as separated, f of x plus f of kx. And now from the previous so from our induction step, we already know it holds, the property holds for k, so therefore that would be equivalent to f of x plus k f of x, and ultimately that would give us k plus 1 times f of x, as we wanted to show. So that completes our induction proof. Now in the third step, we will just take, let's say, take y equals minus x and substitute it into our expression. So observe that 0 is equal to f of 0, obviously. So we found it in our first step, and I can rewrite 0 as x plus minus x, and then I will apply the definition of the function f to rewrite it as f of x plus f of minus x. So that will clearly imply that f of minus x is simply equal to minus f of x. So from here one can also obtain that, so noticing this property here, consider the following expression, minus kx for natural numbers k. So this expression can be, well, obviously we can, by this result here, we can take out the minus sign. So we have minus f of kx, but then from the previous step, in the second step, we already know that this expression, in this expression we can take out the k as well. So we will have k f of x. So this result holds for natural numbers k, and therefore our result is generalized. So therefore let me rewrite it as follows. So therefore we were able to generalize the result from the second step, which only holds for positive integers, onto the whole set of integers, k and x for all rational numbers. So in the fourth step, we will take the x is equal to 1 over k. In this case, we get that f of 1, which can be written as f of k times 1 over k, is equal to, I can take out the k, f of 1 over k. So as a result, that suggests that f of 1 over k is simply equal to 1 over k, and then so that k moves to the left hand side, times f of 1. And finally, in the fifth step, for m in integers and n for natural numbers, we know that f of m over n, which is a rational number here, is equal to, I can take out the m. We already know from the third step that for integers m we can take it out, 1 over n. But then from the fourth step, we know that f of 1 over n is simply 1 over n times f of 1. So therefore, we get m over n times f of 1. And therefore, so that's if you call for m over n is equal to q. So that's kind of equivalent of saying that f of q, q being a rational number, obviously, is equal to f of 1 times q. So we get a linear form, and that's our solution. Some textbooks they write the solution in the following form, which is obviously equivalent. C is a constant here, with that constant c is equal to f of 1. Obviously that's an equivalent representation of the same result. In the last step, so it is just a matter of simple practice to notice that it is easy to check that this functional form actually satisfies this constraint given in the problem. So let's have a look at it together. So we have c of x plus y. I can go ahead and split it, so it would give us cx plus cy, and therefore cx is simply equal to f of x, and in a similar way c of y is simply equal to f of y, and sure enough f of x plus y is equal to f of x plus f of y. That concludes our proof. I would like to make a note here that this proof only works for rational numbers. In fact, we cannot generalize it for a function from reals to reals. In that case, we will have a whole bunch of not continuous, discontinuous functions which also satisfy this condition. We need, in a sense, in order to further generalize it for functions from real numbers to real numbers, we will need some extra conditions, as I will show in my following step. But hope you enjoyed the video. See you in our next lecture.